And the fun thing is your clock slows down, your biological clock slows down. If you've got, your 3-year-old child back at home, if you carried on doing that, you'd end up younger than they are.
My name is Nick Nagaka and you are locked into Culture TV. For the culture, by the culture. Let's go. Eamonn.
Hi, Nick.
Thank you so much for coming down, mate.
Oh, pleasure. Thanks so much.
How are you?
I'm not too bad, not too bad at all, yeah.
So, explain to me what your role is, because I know you work at Jodrell Bank, which is one of the biggest telescopes. Is it the biggest telescope in the country?
It's, I guess it's a special kind of telescope. It's not like one you look through and see directly, so it's a radio telescope.
A radio telescope, yeah.
But it is the biggest radio telescope in the UK, and actually it's the third largest radio telescope that you can steer in the world, even 60 years on or so since it was built.
Wow.
Yeah.
So what do you do there?
So I'm unusual in that at Jodrell in that I normally use optical and infrared telescopes, and I use those to look for exoplanets. These are planets that orbit other stars, so stars other than the sun.
Right. And how's that going?
It's amazing, actually. It's a pretty young field.
Yeah.
And the first planet around another star was found mid-90s, so like 25 years ago. And now we know of well over 4,000, with thousands more that are kind of waiting to be confirmed. So it's kind of really, in our own solar system, we know there's 8 planets.
Yep.
Now we know...
I thought it was 9.
There did used to be. Yeah.
Pluto.
Poor old Pluto, I'm afraid.
Pluto out of the planet game?
I'm afraid Pluto's being demoted. It's been relegated.
So what's Pluto? A dwarf planet? What's it called?
You got it right. So dwarf planets, and we now have 2 types of planets. So we've got your bog standard planets, and then other planets known as dwarf planets. So what's the difference between those?
Halfway between a moon and a planet.
In essence, that is part of it. So ordinary planets, first of all, they have to orbit a star, in our case, obviously the sun.
Yeah.
Secondly, they have to be large enough to be spherical in shape. So that kind of rules out things like comets and that are too small, their gravity isn't strong enough to make them round. And then lastly, they have to be large enough locally that they're the biggest thing in their own orbit, so they clear their orbital path of all the small guys. Okay, so Pluto falls on that one. It's essentially a part of what's known as the Kuiper Belt. There are thousands of objects out there at about the orbit of Pluto. Some are even the similar size, perhaps even bigger than Pluto.
Yeah.
And either you have
in the Kuiper Belt.
In the Kuiper Belt,
which is.
Think of a big asteroid belt beyond the orbit of Neptune,
beyond Pluto.
Furthest standard, and Pluto, so basically out there.
So it's almost like a ring around our solar system, isn't it, of crap?
Exactly, yeah. So we've got another asteroid belt between Mars and Jupiter. Mars
and
Jupiter.
I told you I'm a geek on this stuff.
You are. You're as clued up as I am, I think so.
And that's mainly ice, that one, isn't it?
That is, they're sort of rocky, icy bodies. There is another dwarf planet in that asteroid belt called Ceres. Yeah, that's the largest asteroid. It's big enough to qualify as a dwarf planet. So it is round, so it's massive enough to be round, and it orbits the sun, and so it's a dwarf planet. Wow. So we've got Pluto, we've got Ceres, and there's a handful of other dwarf planets out beyond the orbit of Pluto.
Right. And when you're searching for planets how often are they cropping up?
More and more regularly. So what is it, 25 years, we've now got 4,000 planets confirmed, and probably as many again that are kind of waiting confirmation. And I think by, within 10 years, we'll know of 40,000 planets. It's kind of accelerating, several a day on average. And as our techniques grow and gain more sophistication, and as we think of smarter ways to find them, we're just finding more and more. We basically now know that wherever we're capable of finding planets around a star, we find them. So our conclusion right now is that every star hosts planets. They're just everywhere.
And is this just within our galaxy you finding planets at the moment?
We have, in theory, got the capability of finding planets in other galaxies using a technique known as gravitational lensing, but that's about it. The planets we've found so far are in our galaxy, and mostly actually in our kind of neighborhood of the galaxy. The galaxy, it's several 100,000 million stars spread over 100,000 light years. We're finding them typically within a few thousand light years, most of them. Although using this gravitational lensing technique, that allows us to find some that are further away.
So the way you find them with this, correct me if I'm wrong. So you monitor a particular star and it is the dimming of the light around that star that enables you to tell if there is an object passing by it.
That's absolutely, that's probably the main method we're using at the moment. That's called the transit method, and it's pretty incredible when you think of the engineering challenge in that. So the most successful telescope we've used so far is a space telescope called Kepler, using exactly this method, right? So, and if you think of our solar system, Jupiter, the biggest planet in our solar system, if that was viewed from far away and it passed in front of our sun, it would block out 1% of the sun's light. Okay, so you'd see 1% change in the brightness of the sun. Okay, that's not very much, but it's detectable. The Earth would be 100 times less again, so 1% of 1%.
Wow.
So that's quite tough to see that kind of level of change. So when they had to build Kepler to be sensitive enough to see that kind of change, and if if we could take the Kepler telescope, put it halfway to the moon, point it back to Earth, and you imagine, Virus Syndicate, you're playing a gig in front of 10,000 festival goers, they've all got their mobile phone torches shining in the sky. With 10,000 mobile phone torches, Kepler could not just see that faint glow, it could tell if just one of your listeners turned off their mobile phone torch.
Wow.
That's what we're talking about.
Wow.
Yeah.
That's incredible.
It's amazing. I mean, I'm working it, but it still blows me away.
Yeah. So this telescope, essentially, it can detect planets the size of Earth. But what I don't understand is how does it, because I know we see a lot about the Goldilocks zone and potential habitable planets. How do they know the distance from the sun or its particular star that it's evolving around? Because it has to be not too far, not too close.
Absolutely right.
In order for it to sustain life.
So that's a great question. So there's a number of things kind of we need to know there. So first we need to know how hot is that star? Because the hotter it is, the further away the planet would have to be to stay in that Goldilocks zone where you could have liquid water. It's not going to freeze over. It's not going to boil away, right? So we need to know how hot is the star. And we need to know, like you say, how far away is the planet from its star? So amazingly, stars, they seem like complicated, but there's actually a fairly simple set of physics. You've got a ball of hydrogen gas literally trying to blow itself apart like a nuclear bomb, and all that's stopping it is gravity, keeping it packed together, and you've just got the balance between the two. So the physics in that is actually a fairly simple system, and so we can use fairly standard kind of school physics to understand how hot something like that gets when you balance gravity against the size of the mass, the nuclear energy. So we know how hot these stars, and we know the hotter ones look bluer, like a blue flame is hotter than a red flame, right? So we can use its color basically to tell us how hot it is.
And the infrared telescope can tell you the color of it.
Yeah, absolutely. If you need to observe it in a few different coloured filters, whether it's infrared or optical or whatever. And the way these stars emit, they're very characteristic. They peak at a certain temperature, and then their brightness falls in a very specific way at any other temperature. So once you get a few points on that curve, you can draw the curve and see where the peak is and know how hot it is, basically. So that's how hot it is, and then how far away is the planet. So for that, we need to know how massive is the star, and the more massive it is, the more it's going to, the shorter the period the object is to stay in orbit. It's going to have to go quicker around the star, right?
So it's the distance between the time. Let me explain this right so I don't sound stupid. So the time it takes for the planet to dim the light, or how often it's dimming that light.
You got it, exactly.
Dictates roughly where it would be in relation to that, depending on the size.
Exactly. So this is what Kepler's laws tell us.
I should be a scientist.
Well, you are a scientist. Just if you think like that, you are a scientist, right? Just because you're not getting paid to be a scientist doesn't stop you being a scientist, right? So that's Kepler's laws. That basically the how far away the planet is from the star determines its period, the time it takes to go around the star. And the further it is away, the longer it's going to take. And also, the more massive or the less massive the star is, the longer it's going to take. So it's those pair of quantities that tell us.
So you take all of that data, and that roughly pinpoints where this planet is in relation to the star, which would dictate to you whether that is in the Goldilocks zone or not.
Once we know the temperature of the star, the amount of energy it's pumping out, its luminosity, and we know the period of the planet, then basically we know what the temperature of the planet is going to be, give or take whether there's an atmosphere and how much that atmosphere is going to trap energy, like we know our atmosphere does.
So how do you then determine if it, because I'm reading a lot about planets that are rocky planets, which is what they say we need for life.
Maybe, but it works. We know it works here.
Life as we know.
Yeah.
I mean, there might be some sort of weird sort of gas creatures or...
There could be, and in fact, even in our solar system, we're thinking about like moons around,
like Europa,
like Europa. So all about this clearly, but just to explain, so Europa is like anybody who's a Star Wars fan might know of. In Empire Strikes Back, there's the world of Hoth, which is like an ice world. And so Europa is like an ice world. It's solid ice on the surface, but we see cracks. Yeah. We see vapor being ejected in between those cracks, and it's basically water vapor being shot out into space. And we know now that underneath that ice, maybe 30 kilometers underneath that ice, there's a sea of ocean. It's ocean beyond that. Yeah. And that ocean... It's basically water, and there's other chemicals in there, and basically you wonder, well, how can there be water? And the reason is because those moons, they're orbiting a massive planet. Their orbit isn't perfectly circular, so sometimes they're slightly closer, sometimes they're further away, and so the gravity on them the gravitational pull on them is changing all the time, and it's kind of stretching and straining them,
and that's creating heat,
creating the cracks, and keeping that water in its form. So the interest is, might there be a situation like we see on Earth where there's life on the seabed near these sort of volcanic vents that doesn't need sunlight at all? Its whole ecosystem is based on geothermal vents, and you could have that on a moon like Europa. So there's a lot of excitement about whether you could find life of that form, subterranean life. Yeah. And then at the other end of the scale, there was recent fuss about Venus.
Yeah, Venus.
Oh,
I've seen something about what. So explain that.
So
isn't it way too hot?
Its surface is way too hot, right? But up in the clouds, it's cooler.
Right.
So there was a team of scientists, and actually my colleague Anita Richards was part of the team. She and I are based at the University of Manchester, and it was led by a colleague of mine, Jane Greaves, at St Andrews. They conducted some observations using millimeter wave telescopes, so kind of between radio and optical, and they detected evidence for a chemical phosphine in the atmosphere. Now, it is still being debated just what the level of that detection is. Some thought they could explain it away. They still stand firmly that there is a detection there that's quite significant. And the thing about phosphine is, here on Earth, the main source of phosphine is life. It's not a very stable element either. We wouldn't expect very much phosphine to exist in Venus naturally. In fact, it's hard to think of what the processes would be. So
what sort of life would be creating that?
Well, firstly, microbial. We just got to take a step back and say, first of all, they're doing more work to try and make sure that they know what that level of phosphine is, that it really is there, and in how much amounts. If it really is there, you've then got to look at what kind of processes could possibly cause that. We don't know of any yet on Venus that would cause it, but it just might be that there's a lot we don't know about Venus, right? So, but if they rule out other forms, if they're forced to look down a route that this might be the result of some kind of biology, you'd be looking at potentially some kind of microbial life. This team kind of put a companion paper out to show how some sort of life system could exist in the clouds, and
could it? In theory,
they've put forward a potential. So in theory, perhaps, right? We don't know of anything like that here on Earth, though. But they've put forward a mechanism by which, who knows, it could. But
compared to if the clouds are quite dense, perhaps bacteria could form around the clouds.
Yeah, and the winds basically keep them at a certain height, and so on and so forth. So I'm not going to pretend to be an expert in biology. It's not my field, but they have members on their team who study that kind of area, and they've said, this is not completely outlandish. Yeah. What it is showing us, though, whether that detection holds up or whether it doesn't, what it's showing us is it's stretching our mind about how life can exist, how resilient it is, the different kind of configurations. We're now thinking about subterranean life on Europa, possibly superterranean, above the ground on Venus. So, we're kind of beginning to realize that life could take all kinds of different forms. It's not just two arms, two legs, or whatever. Yeah.
Do you think it is a matter of time before NASA tells us there's life on Mars?
I'd love to think so. I want
there to be so much.
I mean, there is, certainly Mars is really interesting in some respects in that we do see evidence even for flowing water, tiny amounts of flowing water at certain times of the year, because the ice there is very salty. So even at the very low temperatures on Mars, it can for certain times of the year go into.
It can get up to like 5 degrees, can't it?
Yeah, possibly. I think most of the time it's well below zero, but because of the composition of the ice and the high levels of salt compounds in the ice, its freezing point is somewhat less than the typical ice here on Earth.
Okay.
And obviously the pressures also are very different. Okay, the freezing melting points of water here on Earth are determined, 1 by temperature and 2 by atmospheric pressures. They're two things in combination. So those things are different on Mars, and they do allow at certain times of the year small amounts of flowing water. Whether there's life now, obviously there's a big question about whether there was ever life, because even if there isn't life now, if any of those probes turn up evidence that there was once life and that it was independent of our life, this is the next door planet to us. This tells us immediately that life takes hold everywhere, very easily, and is probably wherever it can take hold, it does take hold. It would tell us immediately, that the universe is probably teeming with life.
Yeah. Because even subterranean, like we're talking about subterranean, it could quite easily be, not easily, but it's quite possible that they may want to go under the surface a bit more on Mars, that they may find things there.
Yeah, it's
even bacteria or microbial life or anything. It could. What was I seeing now? That didn't they find an asteroid here or they found some debris here that they believe came from Mars, and in that was fossilized bacteria.
Yes, well, so they've had to rise back. There was a big thing in the early 90s, and I think President Clinton came out with a big statement. So there are a few examples of rocks on Earth that have been found. This was one of them, the Allen Hills meteorite, and they have come from Mars. Basically, something has pounded into Mars, sent a load of ejecta out into the sky. Some of that has escaped the gravity of Mars, and just by chance, occasionally one of those lumps comes into Earth, and if it survives our atmosphere, there it is on the ground. So they found, and they can determine from the composition that it's not earthly, it's not from the moon, it's from Mars. And like you say, there was evidence inside one of these meteorites of something that looked kind of worm-like.
Wow.
And they sort of thought, well, it looked just like a similar kinds of type of life forms we see here on Earth. So there was this big statement that it looked like evidence of true alien life. And unfortunately, since then, there have been demonstrations of how natural processes can cause similar looking features in the rock. So you got two explanations, and in science, whenever you have competing explanations, you should take the most boring one, because extraordinary claims require extraordinary evidence. That's the way we have to work. So so for now, the working assumption is it's probably a natural process.
That's the shit thing about science, isn't it? Because you've always got to go with the most obvious, boring explanation.
It's so, and maybe that's wrong sometimes, but whenever it is wrong, further evidence will out it, right? So if you didn't do that, if you didn't go to the most boring explanation, we'd soon end up in a right shithole, right? with what our understanding
living
about
in
the
chaos,
universe.
wouldn't we?
Absolutely, complete madness. So you've got to buy, and sometimes I see results that look very exciting, and I want to get really excited about it. And all scientists go through this. We've got to take a step back and go, okay, is there something much more boring that can explain this? And that's the bane of our job, really.
So about 4,000 exoplanets that have been discovered in the last 25 years. How many of them lie within the Goldilocks zone?
Well, so the most common, so quite a lot of them, and this is because many of them are being found around the most common type of star,
which is similar to our star.
Which is a bit smaller than ours. Our star is a brighter than average star. Most stars in our galaxy are maybe about half the mass.
Right.
And although they're half the mass, they're much, much dimmer. As you shrink the mass, the brightness of the star ramps down massively.
Oh, really?
So they're really quite faint, thousands of times fainter than our sun. And so we see a lot of planets that are actually very close to those kind of stars on really short orbits of a few days. And those are in their Goldilocks zone because they're around a really feeble star.
Right. Okay.
So an example is about.
But would gravity not be considerably different on a planet like that?
Well, the planet itself, the gravity will be determined by the properties of the planet rather than its star. Like, our sun, it affects our tides and stuff like that, but it doesn't affect how you and I walk around. That's the Earth's gravity.
Okay.
So there's a nearby star system called TRAPPIST-1, and around that, astronomers have found 7 Earth-sized planets. They're all about the mass and size of the Earth, and 3 of them are orbiting in the Goldilocks zone, this zone where they could have water on their surface. And so that's a really exciting discovery. And although it's fairly unusual, it's the case that maybe even half of stars of that kind of size seem to host stars that are potentially within the habitable zone of that star.
Would Venus be perceived as a planet within the habitable zone if you were to look from afar?
It's right on the edge, actually. A little bit further in. In fact, Earth is close to the edge. Earth is not far from the inner edge of the habitable zone. I mean, this is why we have it. Basically, is part of the climate change issue. The reason we are so sensitive to stuff we're dumping in the atmosphere is because we're on the edge of the habitable zone, and if we warm up our planet too much, we cross that edge. That's
it's a very fine balance.
It's a very fine balance. So Venus is even further in, and the thing about Venus, it's shrouded in a very thick atmosphere. So the temperatures on the surface are 300-400 degrees Celsius. It's hotter than Mercury, which is even closer to the sun.
Really?
Yeah, because it's surrounded by such a thick atmosphere. Mercury has no atmosphere.
Right.
So Venus is where is the runaway greenhouse effect that we don't want to end up being like. So.
Yeah, because I've seen that's quite a big agenda of yours, isn't it? In terms of climate change and something that you're quite concerned about.
I think most rational thinking scientists, most rational thinking people are worried about it, right? So I mean,
I think the thing is for me that I mean, the reality of climate change in my day-to-day living is hard to see.
Yeah, no, absolutely.
So when I'm just getting up, I'm going to the gym, I'm walking my dog, I'm coming here, I'm flying, or whatever I'm doing.
Yeah.
The reality of the planet heating up, the possible disastrous effects of that are hard to compute into your daily existence.
Absolutely.
and to be bothered or scared of that.
I know. It's kind of like the people on the Titanic, the hour before they hit the iceberg or whatever, and the captain is probably shitting bricks at that stage, and everybody else is going, what's the problem?
Would you compare that's where we're at?
In a way, it is. The scientist. I mean, I'm not a climate scientist, but climate scientists I've met are genuinely frightened about what's happening. I mean, they can see all their data. It's beyond debate. It's been beyond debate for some time that there's no doubt that the amount of carbon dioxide and methane, which is caused by large-scale farming practices and stuff like that, it's heating up our planet. And we can still have cold days, but what happens here in the UK or in Salford or Manchester, that's not the issue. It's what's happening globally. And globally, we're smashing record after record after record. The top, I think I'm right in saying the top 20 hottest years are pretty much, almost all of them are from the last 20 years, except 1 or 2.
Wow.
We really are.
And what are the consequences of this long term?
Well, it doesn't take much of a change globally to change weather patterns markedly. And once you change weather patterns, countries that might have had a nice, pleasant climate will suffer, severe droughts or severe floods or things like that. And so, that's you're going to. I mean, obviously, hopefully we're going to do things to change it, and I think we are beginning to do things to change it. If we did literally nothing, you would find, large areas of the world becoming uninhabitable. Food production would collapse in many areas. The ecosystems of many ecosystems of life would collapse.
Yeah.
And we're top of that food chain, right? We devour the animals that devour other animals, and insects and bugs and bacteria and so forth. We need it all. We're at the top of that pyramid, and when someone's pulling away bricks at the bottom of a pyramid,
which will have social and economic problems, which will ultimately
take your pick,
takes into wars and whatnot.
It's not going to be good. But the thing is that we can change. I'm always an optimist. The message might sound bleak, but actually, on the flip side, what an opportunity if we harness solar energy, if we harness wind power, if we harness hydroelectric power, if we harness geothermal power, if we master those, and we are beginning to master those, that's cheap electricity to do with what we like.
But it's essentially solar power is free.
I mean, it is. We got 5 billion years of free power up there. That's we just need to harness it, right? And we can harness it on whatever scale that our technology allows. So if we kind of short term, if we do those changes, and I just think simple. Well, I say simple things, but imagine if businesses were audited for their energy use in the way that they have to be legally, financially audited, right? Everybody's got to tot up their incomings, outgoings. So if that was true, if they were audited for energy legally, and then there was taxation on companies that didn't deliver much profits but used a lot of energy, and so that you looked at your profits per unit energy, and if that was the way that stock markets were evaluating everything, it would just change everything, right? It would those companies that were maybe removing CO2 from the atmosphere, making positive changes, they would be our gold chip top companies, most valued. So
the problem we have is we live in a capitalist society.
But that would be a capitalism, just a different form of capitalism. Capitalism where instead of money, which kind of is illusory, right? What is money? It's a promise, blah blah blah. But if that money was backed by, if money was dependent on making a positive or a negative change to energy use, then so energy becomes money in essence.
Okay, I'm with you.
And then it's all aligned, right? So you
could almost have a cryptocurrency monetized against it, couldn't you?
So I think it's not crazy at all to do something like that.
No, it's a big. Well, people are creating currencies monetized on the potential of a business that is a white paper, doesn't even exist.
Exactly. It's a promise to give gold, which they don't even do anymore, right? That got abandoned decades ago. So it's just a trust thing, right? It's a piece of paper. It's a form of trust. It's a bond of trust. That's what it is. And there are other ways of doing this.
And energy is actually tangible.
Energy is, it's a real world thing. It's a real form of accountancy about, what
possibly
you're using.
the most valuable.
It is the most valuable, right? That would be my take.
What would we be? I mean, look at this room. We've got aircon, we've got lights, cameras, microphones. You could have all of that. You turn the power off.
Yeah. That's
it's
it.
redundant.
So as we get more and more technological, our lives are so dependent on, always has been dependent on energy, but you say what visible impact, look around you at the technology. That's energy. That's a form of energy that we've managed to control and to harness. And I think we should monetize it so that businesses and everything are just aligned that way to do good and are credited when they do, and they're taxed to hell when they don't.
Yeah. I think it's a good idea. I think we do need to be more responsible for, I've got a 3-year-old little girl.
Yeah.
I want her to live in the best possible environment, in a healthy, thriving planet, not a dying, overheated.
And it's not a compromise ultimately. It's a big change to our lives, but once we do harness these other energy sources and we're not impacting the environment in a way because of those energy sources, sky's the limit then. We can do all kinds of stuff. We can really let go without having to worry about what impact it's making. So
without getting too conspiracy theorist here, but have you heard of Bob Lazar?
I have.
If what he says is true, they already have this.
This is Area 51, right?
Well, they're saying that they have that they uncovered an antimatter reactor that feeds itself. It's basically, it could power an entire city. For eternity.
Yeah, why aren't they using it? Why don't they just have?
Well, they're saying it's alien technology. That's the.
Yeah, look. So I'm not a UFO expert, but I'm kind of an outsider in that sense. But all I would say is, one thing that's different now than 20, 30, 40, 50 years ago, and there's been UFO sightings all that time, is we've all got these, haven't we? We've got phones with pretty smart cameras on them, and it's kind of amazing that we're not yet seeing that irrefutable phone picture of a UFO. Well,
the reason for, if you believe Bob, right? If you believe in Bob, okay. So have you seen the Tic Tac videos?
I know about. I don't think I've seen them, but I know the fighter pilot videos. So the Pentagon have made 3 videos public officially.
which are of crafts performing insane maneuvers.
Yeah.
And they say they are operating intelligently.
Well, they're not fully established as crafts doing insane maneuvers, right? They're lights, which if you interpret them as graphs, must be doing insane.
So I think what the official thing that they're saying is that it's physical. That it's definitely an object. It's definitely a physical object, and it's moving in a way that you would say is definitely intelligent.
Okay, so. As I say, I'm not an expert. I'd have to see what the evidence is that it really is a physical thing rather than say...
Oh, no, because it's come up on infrared.
Cloud mirage or whatever it is. Okay,
yeah.
So, but I would just say, why is that kind of grainy evidence our top evidence in an era where we have cameras everywhere?
I totally agree.
You know,
and I think
this
is the argument that everyone, and rightly so, puts forward is we live in an era where we all have these. Why are we not seeing them? So, which will bring me to Bob's story, right? So if you believe in Bob, so what Bob says is that these crafts that they've created. Now I know this sounds crazy, but this is his story.
Sure. Yeah.
So he's saying that they essentially control gravity, gravity waves. Okay. So when you perceive it, it bends light, everything around it. So if you see it from certain angles, from a certain angle it might look like a donut, from another angle it might look like a disc, from other angles you may not be able to see it at all, depending on how these gravity waves are being emitted around the craft.
Okay.
So I'll send you the video on it where he explains it.
Yeah, that'd be cool. But so he's kind of giving this story that they're kind of cloaking themselves in some way.
Not necessarily intentionally, it's just saying it's the way the craft operates.
Okay, but it's still the case, isn't it, that they're managing to cloak themselves from pretty much every mobile phone camera in the world, but not a grainy tic-tac sort of
infrared camera.
It's like, how come? You know, it's
just... Yeah, no, it is a great point. And this is why, I mean, I am intrigued very much by, like, for example, the Bob Lazar story, the tic-tac videos that have come out. I find them very interesting.
Yeah.
And the thing is that's quite interesting is that the Bob Lazar story came out in 1990. The way he describes how these things operate is exactly how the videos that the Pentagon have released. The two stories do marry up if you were to look at that.
Yeah.
So there is 50% of me that thinks, is this real?
Yeah.
There's 50% of me that is also, why is there no real footage? Why is there something that we can't see more clear? There's 8 billion people on this planet. 5 billion of them have iPhones or Androids. Why are we not seeing something more clear? It's a tricky
thing. So, I mean, as a scientist, I normally deal with data that doesn't have a dog in the race. That, you know, in the sense that there's no, you know, it doesn't care what you think. The data is there. You make the measurements. You infer the stuff. Whereas in something like UFO sightings, etc., the problem is a lot of data clearly is dishonest because there are people who want to fraud stuff. Yeah, so there may be, you know, I don't doubt there are some genuine observations that have been carefully taken, and the people who've collected them have collected them honestly and don't understand what they are and want an interpretation and you know, that's really interesting, right? But you've got to because there is this swarm of dishonest data, you've got to be almost like a criminologist, you know, be able to filter out.
Exactly.
You know, it's almost a different skill than
I would
science.
only look at the official data released by. So they've got a thing called ATIP now, which is a program set up by the US Navy, I think, in the Pentagon in 2007, which is it's called Advanced Aerial Threat something. Anyway, it's been running for about 15 years, something like that, where they're monitoring anomalies in the air and looking to find, you know, rational explanations for them, and in most cases they do. But there are, I think there's 140 cases since maybe 2007 which they have no explanation for. But
even there, you would say, is there a reason for them to suddenly release all this stuff? Are they testing drones? Are they testing unmanned vehicles? And they're quite happy for there to be a whole sort of UFO smokescreen around that. So do they have a vested interest as well?
Yeah. So I mean that would make a lot of sense, wouldn't it? Because then if you're looking at, like, rivals like China or Russia. You've got a brand new drone coming out that's going to be able to take over the whole world.
So a UFO smokescreen around that is convenient, right?
Yeah,
so,
of course it is.
So you've got to, again, that's what I'm saying, you've got to almost you've got to have this level of suspicion with all data, and it makes it really, really difficult then to get to the truth. So I'm not saying it's all rubbish, because I don't know that. But what I am saying is I don't really have the skills to investigate stuff like that, because it's intrinsically, it's much of the data is intrinsically dishonestly constructed, and that's a very different field to the field I work in.
And I think it's either, with that whole UFO thing, it is full of nut jobs.
Yeah, which unfortunately,
which is the problem with it. Because if there is any anomalies out there that are exciting, or something that we do want to take seriously, no one's ever going to give it that chance to take it seriously, because it's clouded with lunatics.
I mean, to me, there are two kind of, unless there is a single race of aliens that have visited us and they all have that same technology, if it's, if intelligent life is common, then you might have expected these different UFO sightings, if some of them are true, to represent different civilizations or whatever that would have different technology. Now, in that case, you would just expect that even if one of them was cloaking itself, another one wouldn't care, or they'd either if they've got really advanced technology, they'd either do a proper job and nobody would ever know whether they're sitting in a fighter aircraft or anything else, or otherwise they wouldn't care that we know, and there'd be phone footage anywhere. I'll
tell you what, we've actually got an opportunity to debunk Bob Lazar right now, because you are an exoplanet researcher. Okay, so according to Bob Lazar, according to the briefings Bob Lazar said he was given, was in these briefings it said that they recovered this craft, however they recovered it, and they believe it to be from a binary binary star system called Zeta Reticuli, which I think is only visible in the southern hemisphere. Are you familiar with that binary
Not
star
that particular system. I mean, there's 4,000 of them, so I don't.
Okay.
Yeah, but I can certainly look it up. I can certainly look it up.
Can you?
So, if we know of a planet around, I mean, I presume if Bob Lazar's been clever, he's chosen a planetary system that we already know about. Otherwise,
I think it was previous to the research, previous to them finding planets, which was 1989, 1990.
Right.
But I did look into it. I have looked it up, and apparently there isn't any planets around Zeta Reticuli.
I mean, to be fair to Bob, that doesn't rule him out, because we don't always see planets around. It depends whether they're giving a signal for the methods we use, and so we're still blind to a lot of planets. Okay? I'm not trying to say so Bob Lazar is true, but because I'm
keeping Bob in the fight here.
I am incredibly skeptical, but I want to be fair. Okay, so a lack of a signal around that star system doesn't necessarily prove he's wrong, unless it's clear that our methods would have found such a planet. Okay.
So back to TRAPPIST-1.
Right.
So there's 3 was it 4 you said?
3 in the habitable zone.
3 in the habitable zone.
4 others, so 7 in total that we know about. So
that means there's a 1 in 3 chance, possibly, that... Not a 1 in 3 chance. There is a possibility that one of those 3 planets, or possibly all of them, could have life on it.
Yeah, it's a possibility. I mean, then we get into all the other unknowns, right? So we don't yet know whether there's water on the surfaces of any of those planets. We don't yet know to what extent water is essential for life, full stop. We know it's essential for life here on Earth. Is it necessary for life on other planets? And we don't, how does life take hold? Blah, 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 blah. All the stuff we don't yet know in science about the ease with which life might... I mean, people often say, and I kind of feel it myself, but I realize it's not a scientifically grounded opinion, that it's inevitable, isn't it, that there must be life out there because, hey, there's life here and there's lots of planets and blah, 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 blah.
I mean, in theory, you'd think that.
You'd think that, and there's lots of stars and so on. But, when I discuss this with colleagues, some of them will point out, well, we just don't know how easy or hard is it for life to take hold of in the first place. We could have been the result of the most unimaginably impossible fluke that happened here.
Oh, God.
Or God or whatever. So, but a fluke of some kind, divine or scientific or whatever, right? So, and this could be it. So it's like a lottery winner thinking, well, hold on, I've just won the lottery. It's tens of millions to ones against I should have done that. Maybe I have a special power.
Yeah.
Well, we know they don't have a special power. It's just that lots of people play the lottery. Almost every one of them lose and one of them wins. So it could be that there are conditions that are right on many, many planets out there, but the lottery took place here, but it hasn't taken place anywhere else. So that could be it.
Even a 1 in 10 million would still mean
that would still mean the universe would be flooded with life, right? So there are, just to paint the numbers, our galaxy, which is, the sun is in our galaxy, this spiral galaxy of several hundred billion stars. Billion. So several hundred billion stars. And we know that
in the Milky Way.
In the Milky Way, and practically every one of those has planets statistically, given the ones we already have found.
Good. Wow.
Anytime we try and look for planets, we're usually finding them. So, and then our galaxy is one of several hundred billion galaxies in the observable universe. So multiply all those numbers together. The number of stars is 1 followed by, or a number followed by 22 zeros in the observable universe. So it has to be such an amazing fluke for life to take hold here on Earth, yet not elsewhere. So it sounds intrinsically like, get away from here. That can't possibly be the case. But until we know what it is that kickstarts life, we can't rule out the fact yet that it could have been such a fluke. I mean, we've got no measure of how how that happens. But I'm an optimist, and I feel like there's just bound to be life out there.
If you were to bet, where would you bet?
Oh, I would personally, and this is not a scientifically formed opinion. This is gut instinct. I'd bet a large sum of money that there's life, and I'd bet a reasonable sum of money that there was more than one form of intelligent life in our galaxy. But I think it's rare.
More than one form of intelligent life.
Yeah. So I don't doubt that we are alone right now by intelligent, like something that's capable of some form of technology, something we would recognize as intelligent.
So even if it was bashing rocks against the tree
even better than that, I'd say, maybe mastering electricity, something like that.
Oh, really?
Yeah, I just feel like, my gut instinct
are so fought towards it in terms of volume of stars versus planets.
But
in the habitable zone.
Yeah, all of that, but there's the big unknown about how easy it is for life to take hold, and I've not got a clue, and no one has got a clue. So, but I'm just an optimist, I guess. I'd find it just very sad if we were it, right?
Yeah, it's lonely, isn't it?
Yeah, it's just crazy.
I really want it to be. I've been like a UFO geek forever. I think I want there to be aliens here. I want them to have come here. I really do. I know it's unlikely that they have, but I want to believe the stories.
The cool thing, though, actually, was my gut instinct is there's probably intelligent life out there. It's rare, but it's out there. That's my gut instinct. I doubt they've visited us, but the amazing thing is that we are now developing the technology that we could visit them. And that sounds amazing. So right now there's a team of engineers involved in the Breakthrough Starshot initiative. So there's a Russian billionaire. He's invested $100 million in this project. He's got a team of engineers that are developing a stamp-sized space probe that will have a camera on it, all the navigation on it, basically a microchip. And they're going to maybe build thousands of these things, fire high-powered lasers at them to propel them to 20% of the speed of light. So the speed of light is the fastest anything can move, even in theory, according to Einstein's theory of relativity. And it will get to the nearest, if they do this, it will get to the nearest star in about 20 years after launch. Alpha Centauri, So, and there's an Earth mass planet orbiting Alpha Centauri. So they would hope for a flyby picture of that planet. So we'll have developed if they think it will take 30 years to develop that technology, 20 years to get it there, and then 4 years to beam back the images. So
55 years.
55 years maybe we would have flyby pictures of the nearest planet, and we will have developed technology that is interstellar. We'll have put our own interstellar stamp on the universe. Now take that one step further. What's going to happen in 100 years or 1,000 years? Surely
it's impossible for humans to travel like that, though, isn't it? Surely.
It might be impossible for us physically to travel like that, but take this scenario. Let's supposing we're sending autonomous spacecraft to the nearest star system. It's finding an asteroid belt there. It's mining it, building 10 copies of itself and launching each of those to the next 10 nearest stars, and they're doing the same.
Okay.
And so every generation you've got this virus growth by a power of 10 of the number of stars that our autonomous craft find. Within 1 million years or so, our craft will have visited every star in the galaxy. Every star system would know about us.
Wow.
Okay, so... And
is that a good thing?
Well, it may not be, but it does then make you think, well, why hasn't that come back at us? Why aren't we seeing those kinds of things happening? It's inconceivable to me that within 1,000 years we wouldn't be able to do that.
Yeah.
Our galaxy's been around for 10 billion years.
Yeah.
So, you know, our position, our technological position is a blink of an eye.
Because if in theory we could do that, what did you say, 1 million years?
If you had a spacecraft building 10 copies of it, it depends how many copies itself and how many they get to. Yeah.
Okay.
So, but that example I gave, you're talking about 1 million years to.
And how long has our galaxy been existing? For 15 billion.
At least 10 billion.
At least
the
10.
universe is 14 billion.
Yeah.
Our galaxy may be 10 billion. Our solar system obviously been around for 5
plenty
billion.
of time.
Oh, it's absolutely
for
plenty
that
of
to have
time.
happened back to us.
Absolutely. If life is relative, intelligent life is relatively common, unless we are the smartest that there's ever been in our galaxy, or the only example of our kind in the galaxy, it's really tough. And this is something that's known as the Fermi Paradox. Enrico Fermi, a physicist back in the 1950s, a Nobel Prize-winning physicist, basically asked the question, where are they? And that's what he was meaning. I mean, he didn't know the technology that we would be on the threshold of ourselves now, but here we are. We're on the threshold of doing that. And he's kind of saying, kind of really surprising that that's not happening back to Earth. And you might say, well, Bob Lazar is saying it has happened, right? But if we look at other bodies, the moon, we've mapped the moon to meter level precision, right? We know the surface of the moon far better than we know Earth, and the moon has looked the same for billions of years. There's no tectonic plates, no active volcanism there anymore. It's looked exactly, the only change that's happened to the moon is the occasional asteroid or meteorite landing on it, the occasional astronaut's boot. That's basically it. And we see nothing else on the surface of that other than our own probes. Same for Mars. We see our own probes. We don't see any other evidence of anything else. So on the planets that are remaining pristine, there's no evidence of interstellar probes that have hit any of those planets.
That's interesting, isn't it?
Yeah, it's really weird. So that leads some to say maybe we really are alone because there's no evidence. But yeah, I find that kind of weird.
I think that's really interesting about the stamp-sized spaceship, essentially. Because essentially, if it could mine, clone itself, or 3D print itself, whatever, and you did that by the power of 10,
exactly,
every single time.
We can't do it yet, but 100 years, 1,000 years, it's
in theory, why not?
Yeah,
in
absolutely.
Theory, why not?
I can't see any showstopping.
And why has
reason.
that not come back? I think that's really interesting. That is because it should have done.
You would expect it to if life was common. So then you've got the ideas of either we're the smartest, or even we won't be around in 1,000 years to do this because we're stupid enough to blow ourselves up or ruin the planet or whatever it is. So there's this idea of cosmic censorship that life never quite gets to that threshold. Yeah. But we're so close to it now. I don't buy that argument. We are too close for that for me to accept that that's the reason.
Is it the term plexit that you've coined?
Oh, so I gave a talk at the Blue Dot Festival 2 years ago. So it's the Music and Science Festival at Jodrell Bank, and I gave a talk on leaving our planet, kind of about this ideas of what it would take to leave our planet. So and this was in the aftermath of Brexit and everything. So I called it Plexit. So,
I love it. So is that based on terraforming another planet? In theory,
I mean, not necessarily. It was just so the talk was just about the idea of the technology that it would take to. So I was discussing this idea of these stamp-sized spacecraft. It's obviously another thing about moving us to another planet, isn't it? And this is you were saying that. So,
what would it take to move us? Let's say Alpha Centauri. Let's say that planet there. Let's say it's a little paradise in space for example.
Yep.
And it's got beautiful blue waters, nice rocky surface, perfect temperature, 25 degrees all year round, palm trees everywhere.
Yeah.
We all want to go, right?
Yeah, yeah.
What would it take to move us 5 light years away?
I just don't. I can't imagine what it would take to move all of us. I could imagine a situation. So if we think about the mindset of the seafarers of the 16th, 17th century, they were prepared to leave their lives to try and go and find if there was new lands across the oceans that they didn't know any. They'd been uncharted. They basically went with a blank map and a pencil.
Yeah.
So there are always people like that. And so if the technology is there to send them, then what technology would it take? It would either take a technology where we found a propulsion system, whether it was ion drives or whatever it is, that could accelerate a substantially massive craft that can have all the life support systems, carry water or the ability to generate water from hydrogen and oxygen, the food supplies or the means to grow food.
As in linear travel?
As in linear travel, but once you get close to the speed of light, linear travel is not the obstacle that it would otherwise be.
It bends space and time, doesn't it?
So what Einstein came up, Einstein's theory of relativity, so working on the idea that light is the fastest that you can go, he developed the mathematics of what that implies. And the crazy thing is, he showed that nothing can travel faster than the speed of light. So if I'm on a motorway where I'm traveling at half the speed of light, and something passes me at 3/4 of the speed of light, you would think, well, add those up, you get 1 1/4 the speed of light. That car must be traveling at. But he said, no, it can't travel faster than the speed of light. So those two numbers don't just add up together. The maths is a little bit more complex. And so what that means is that because the speed of light stays the same, it's the distances and the clocks that change. Okay, even our body clocks change. So, so if I travelled 99% of the speed of light, just by virtue that I'm travelling that fast, the distances collapse by about a factor of 7. So instead of 4 light years, it's just over half a light year.
So 6 months.
So 6 months. Okay, in theory, if you
could travel at the speed of light.
If you travelled basically at the speed of light, and my clock would slow down.
A penny-sized rock would destroy the ship if you hit one.
Well, I guess if you've got the technology to travel at the speed of light, I guess you've got some other smart technology as well to deal with all that. Some sort of snowplow ahead of you or something. I don't know what. But basically, and the fun thing is your clock slows down. Your biological clock slows down. If you've got your 3-year-old child back at home, if you carried on doing that, you'd end up younger than they are.
Wow.
Yeah, so it's pretty. And you might think, that all sounds great, but how do we know any of that's true? And the reason.
But didn't they test it with the atomic clock?
Yeah, I get my phone out again, right? So you and I got a phone. Probably yours got GPS on it.
Yeah.
So we all use GPS.
Yeah.
And GPS wouldn't be able to give us street level navigation unless they made the corrections that Einstein says needs to be corrected. They have to take account that the satellites are moving in the sky.
Yeah.
And they have to take account that their clocks therefore slow down. They're in a gravitational field. Their clocks slow down according to Einstein's theory. So, and if they didn't make those corrections, they would lose where we are at a kind of error rate of something like several kilometers per day. It would be just totally hopeless to navigate streets. So without Einstein's theory, so we know that it's correct. It's
so in theory,
the best thing we got.
To travel to the future is not impossible. In theory,
we always travel to the future. It's the rate at which we do it.
You just can't travel back.
You can't travel back so far as we know, except, you mentioned the idea about bending space. There's ideas of like wormholes or whatever, but it doesn't seem like you can send. It's
Is time linear? Is it just linear?
We don't know for sure. Our best models of the universe and the way it's evolving, etc., are based on linear time. But it's personal. Time is personal. That's the key thing. That's what people don't always get, right? When we're all in the same place, time seems to move the same for everyone. But when you start accelerating away and moving at speeds to the closest speed of light, or you're very near a very strong gravitational field, your clock slows down, and literally you slow down your aging. So everybody's clock is different. Everybody's meter ruler is different depending on your motion, and so the distances to things change.
Yeah.
So it's linear so far as we understand it, but it's not
in a 3D sense.
It's not
linear.
it's not rigid. Let's put it that way.
Wow. So time is fluid and flexible.
If we could travel arbitrarily close to the speed of light, we could pancake the entire universe to
and gravity
like a sheet.
affects time.
And gravity affects time, etc. Because what gravity is completely equivalent to getting into a lift, cutting the cable, and just carrying on falling. Okay, gravity is then pulling you.
Yeah.
And you think what that looks like inside the lift. Once you sort of got over the terror that you're falling, it's like being weightless, right? It's being out in deep space. So the effect of gravity is the same as you know, it's just accelerating you.
Yeah.
But actually, if you look at the laws of physics in that accelerating frame, it's exactly the same as being out in deep space. So it's indelibly, you know, you kind of get this geometrical view of gravity that gravity is distorting space. Okay, and that's literally what it does. So.
Almost as if space was like a net and gravity is like a ball that rolls around it.
Yeah, it's kind of like that, absolutely.
And so if you've got a ball there, it creates a dent, it pulls things.
Yeah, or you pull a plug out of your bath and watch the water spiral in. That, you know, your water is like the space-time, basically. So, yeah.
So in theory then, I know we spoke a lot about Bob, but in theory, if gravity does affect time, and if you can control gravity, you can control time.
Well, I guess it depends what you mean by control it. Control gravity. I mean, the source of gravity is mass, is energy and mass.
If you could, let's say this phone, you took this, and you could make this operate independently of the Earth's gravitational field on its own gravitational field, but within inside the Earth.
Well, it does have a gravitational field. It's just so tiny that it's unmeasurable because it's billions and billions less massive than Earth.
But if it wasn't affected by the Earth's gravitational field, if there was a technology that could put something around that so that it could do 90-degree turns or whatever without having any inertia effects on it.
But unless it's... so, I mean, if you think of Earth, something even the size of the Earth isn't wrapping light around it. It isn't, you know, bending light around it. I mean, it does to a tiny amount, but not in a way that makes Earth look like it's disappeared. So if this thing really is bending light according to Einstein's theory, it would have to be more massive than Earth.
Right, okay.
So, and a lot more massive than Earth. I mean, even the sun, we can see how the sun, you know, the first verification of Einstein's theory of relativity back just over 100 years ago was basically observing the sun during a total eclipse where the moon passed in front of the sun, and then you could see stars around the edge of the sun. It was like nighttime, even close to the sun. And those stars were in a slightly different position to where they are when the sun isn't there. Okay, so the sun literally was bending their light around, but that was like by a tiny fraction of a degree. Sun. And that's the sun. So, you know, so whatever Bob Lazar is looking at, it's not gravity as we would understand it. You'd have to invent a new kind of extension to Einstein's theory to explain that one to me.
Yeah. This is the thing, once you bring science into these things, real science into these things, you can start really pulling apart a lot of the different stories that are out there.
You can certainly put them to reasonable stress tests. And then, you know, if the data is honest, then there's still something at the end of that we can't explain. Okay? But, you know, usually, more often than not, what happens is the people proposing the data then start going down avenues of conspiracy theories and so on, and then you know that basically they've probably been rumbled.
Exactly. So if you looking at this like this Kepler telescope, is that responsible, would you say, for a lot of the planets that we're finding at the moment?
Yeah, I mean, it's now no longer operating, but it's still probably, it's at least half of the planets that we've found have come from Kepler.
Are you finding them at Jodrell Bank as well?
So Jodrell Bank is involved in looking for, one of the major programs it does is to look for pulsars. These are the remnants of stars that are rapidly spinning, kind of almost at the state of being a black hole, but just at the densest state before you become a black hole. And these are some of these rapidly spinning stars actually have planets around them.
Really?
Amazingly. We don't know whether those planets were originally there with the star system before it kind of blew, or whether it's some kind of debris left from the detonation of the precursor star. But they are planets; they're in orbit about them. So, so telescopes like the Jodrell Bank telescope, certainly are involved in looking for planets such as those. But the telescopes I use are optical telescopes.
Yeah.
Britain is pretty crap for we're reliant on good weather. So we use telescopes in Chile, Hawaii, places like that.
And do you get to travel to these places to use them?
Yeah, I do sometimes. More and more these days, it's remote, so the data just comes to you.
And you analyze it.
You think, damn. But no, I've
pre-COVID, you'd be able to get out there.
Yeah. I've been lucky enough to go to places like Chile, the Atacama Desert, which is like some of the driest skies in the world. There's areas there that don't rain, where it hasn't rained for many decades.
Really?
And when you look up at the sky there, it's in the southern hemisphere, so you're looking towards the center of our galaxy.
Wow.
And many people I meet have never seen the Milky Way. You have to go to a dark sky in the UK to see this sort of milky glow across the sky, and that's one of the spiral arms of our galaxy. Well, from the southern hemisphere, you see the other direction towards the center of our galaxy, and that's astonishing.
Really?
It's just right up there. This glow, you can almost begin to see a sort of browny red hue of some of the oldest stars in our galaxy.
And you can see that from here?
Oh, yeah.
With the naked eye?
Absolutely. I mean, it's just so obvious. It's incredible.
Wow.
It's one of the most stunning sights you can see in the sky, I think. So,
wow.
Yeah.
I've only ever seen, I think I was in Devon once, and I saw part of the Milky Way once.
And it is awesome, right?
Yeah,
it
was incredible.
Yeah.
I've never seen anything like that since. Even when I travel a lot, and I've never seen anything. I was looking for, when I was in New Zealand and Australia just before the pandemic, and I was looking at the sky quite a bit there to see how it looked different, but. Yeah,
you'd see it from there, but you'd have to go to a dark site. If you're in the big cities or whatever, that's the problem. So you'd have to go out in the sticks a bit. But it's worth it if you get a chance to, if you're down in the southern hemisphere, give it a go again, because if you get a dark sky and you look up, man, it's incredible.
Really?
It really is. I've been in the business for decades, and I still, when I see that site, it's
still blown away.
Because you're just thinking that glow is billions of stars.
Wow.
It's like the next.
It's a dust, but it's not actually a dust. Each one of them is a.
Well, and even better, towards the center of the galaxy, you see the glow in between it. It's like cut in two by this sort of band of blackness, and that is dust. That's dust between us and the galaxy, confined to a very narrow plane of our galaxy, and you can see it clearly. It's like it's been backlit by billions of stars in the center of our galaxy. It's mind-blowing. It really is.
Wow.
Yeah.
So how rapid is the technology that you guys are using, developing?
Incredibly rapidly, not just on the engineering side, like telescopes like Kepler and that, but also on the computing side now. The big thing, we're using things like machine learning techniques, kind of forms of artificial intelligence, because we deal with massive data sets. Basically, we're using big telescopes to monitor billions of stars every night, and then using computer algorithms to make accurate measurements of every single one of those stars, and looking for the kind of signals that might tell us there's planets. So it's something that would have been next to impossible only a short time ago, and now it's kind of routine.
What do you think it's going to look like in 20 years?
I think the biggest change actually, I think, is going to be not so much we'll still be finding more and more new planets, but we'll also be, those planets we already know about, we'll be probing their atmospheres. We're already beginning to do this. I've got a team at Manchester which is doing this a bit, but we'll be doing it much more, perhaps more towards Earth-like planets, looking at their atmospheres, finding out what chemicals are in those atmospheres. And when you step back and think about it, we did like that transit method. You're not seeing the planet, you're just seeing that it makes a dip in the light from its sun. And yet, using basically the same technique, you can tell whether it has an atmosphere, whether there's water vapor or something else in the atmosphere. You see what's in the atmosphere. It's amazing, really. We're not even seeing the planet, and yet we can tell that.
And that's how they're getting the data, which is giving artists the ability to give a design of what it may look like on there?
Yeah, once we got an idea of the mass of the planet and the size of the planet,
And
so
the
we
composition,
know,
etc.
yeah, then we get to know the density of the planet, and we'll know whether it's a largely a ball of gas like Jupiter, or whether it's a rocky planet. Once you know the density, you know whether it's like a rocky planet, or whether you can, they are quite different in terms of density. A lot of planets are kind of in between, and so they're hard to tell. Some of them might be gassy, some of them might be rocky. That's still an area where we're still trying to figure things out. But if something has an average density of 4 grams per cubic centimeter, we know it's an Earth-like planet. If it's 1 gram per cubic centimeter, we know it's a Jupiter-like planet. So that's when we actually start to know, does it have a solid surface? And we can probe its atmosphere. Is the atmosphere anything like Earth? At the moment, the planets we tend to look at are the bigger planets, because that's where our sensitivity is. But you ask me about 20, 30 years' time, I think we'll be looking at Earth-type planetary atmospheres. In fact, in a few months' time, the James Webb Space Telescope, Hubble Space Telescope's replacement is going up, and that will begin to do that kind of work on some of the very nearest.
And will you be working on that data once it comes back?
I very much hope so, but it's pretty tough to get a proposal on that telescope in the early days. So at the moment, I'm collaborating with colleagues of mine in Thailand. We've got a global network of telescopes that we're doing this from the ground. But yeah, like everybody else, I'm going to be making telescope proposals, including, I'm sure, on JWST for time to get that stuff. So I hope it's going to be around for quite a while. It's going to be pretty exciting.
Oh, amazing.
Yeah.
Eamonn, thank you so much. This has been brilliant.
It's been fantastic, Nick.
Thank you.
Cheers.